This will be our last lecture on applications of integration. We already talked about in our previous lecture, the fundamental theorem of calculus, that definite integrals give us the area under the curve of a function. We could actually extend that concept. We do know that we can take the integral of this function, this f of x, from a to b, and this will give us the area underneath the curve of f all the way to the x-axis. Similarly, we can sit there and take the integral from a to b of g of x dx, and that'll give us the area underneath this curve, g of x, from a to b. Notice we integrated from a to b in both cases. Well, what happens when we stack these curves? If I stack these two curves on top of each other and align our a's and our b's, notice that I have an area between the two curves, and I want to calculate this area between the two curves. And this is actually a very simple process to do, because I already know the integral from a to b of f of x is the area underneath f of x. I already know the integral from a to b of g of x is the area underneath g of x. Well, notice this shaded region here. This is basically all of f with g backed out of it. So basically, this integral, the area between the two curves, is the integral from a to b of the upper curve f of x minus the lower curve g of x. Now we do make an assumption here. We assume that f is always going to be higher than g on this interval from a to b. So as long as we put the upper curve on top, the lower curve on second, not on top, first, the lower curve second, and then our bounds of integration from a to b, where a is the smaller of the two numbers. Again, we need to know which curve is on top. That's key in these problems. Let's look at an example. Find the area between the two curves y equals 2x and y equals x squared from 0 to 1. Well, I know my area is this function, integral from a to b of f of x minus g of x dx. Well, I'm going from 0 to 1, so what I need to do is I need to find out which curve is on top. Now notice if you plug in 0, these are both equal to 0, so 0 is actually a point where the two curves intersect. So a lot of times we want to plug in a number that's in the interior. Let's just plug in 1/2. 2 times 1/2 is 1, and 1/2 squared is 1/4. So when I plug in 1/2, this y equals 2x gives me a higher y value, so it is the curve that is on top of the other curve. So when I plug in, there's my function, there's a graph of it. Notice this is y equals 2x is the red curve. This is y equals x squared is the blue curve. I want to go from 0 to 1. And y equals 2x is always on top. So when I do the integral, this is the integral from 0 to 1 of 2x minus x squared. This is my f of x minus my g of x, or my upper curve minus my lower curve. Now, once we get to this problem, the setup is the difficult part, because right now we should all know how to do integrals. The integral of 2x is simply x squared. The integral of x squared is 1/3 x cubed, and again I want to evaluate from 0 to 1. This is just a matter of plugging in 1 into this antiderivative, and then plugging in 0 into this antiderivative and finding the difference. And when we do that, this becomes 1 plus 1/3 is 4/3, minus 0, which is just 4/3. Now we do have a special case of this. I'm going to give you a very similar problem. It says find the area of the region enclosed by the functions y equals 2x and y equals x squared. Well, enclosed means between the two curves. So I again want to find the area between the two curves. The issue we have here is that we are not given our a and our b. And the reason we're not given our a and our b is we're actually assumed that we want to calculate this. We want to know where these two functions intersect at. So what we're going to do is we're going to set these two equal. 2x equals x squared. Now this piece right here is a quadratic equation. So I'm going to get everything to one side, and I'm going to solve. So x squared minus 2x is 0. We can clearly factor out an x, and we get 0 and 2 as our possible solutions. If we go back to our graph, we notice that that corresponds to what we saw. These x values, these two functions intersect at 0 and at 2. So we want to integrate. Our a is going to be 0, our b is going to be 2. Again, my upper curve is my 2x, my lower curve is my x squared. So I'm going to take the integral from 0 to 2 of 2x minus x squared. Again, we already did this in the previous slide. This is simply x squared plus 1/3 x cubed. And again, we're going to evaluate this from 0 to 2. So plugging in the 2, we get 4 plus 8/3 minus 0. So 4 is the same as 12/3, and 12/3 plus 8/3 is 20/3. We actually have a formula for average value dealing with integrals. This is a fairly simple formula. It says the average value of a function f of x can be calculated by the following. Integral from a to b of f of x dx. This looks like our area under the curve. But we're going to multiply this by 1 over b minus a. Again, these a and b and this a and b are the same. Let's look at an example of this and see if it makes sense. Find the average value of the function f of x equals x squared minus 4 from x equals 0 to x equals 3. Well, we have the integral of 1 over b minus a, 1 over b minus a times the integral of a to b of f of x dx. Here's my a is 0, my b is 3, and here's my f of x. This is a quick integration. The thing we need to remember is this is going to reduce to 1/3 out front, and when we go to evaluate it, we need to apply it to everything. So when I do the 1/3, I'm going to put extra brackets here and make sure I distribute it into my final answer. And when I evaluate this at 3, I get 1/3 3 cubed, which is 9, minus 4 times 3, which is 12. So 9 minus 12 is negative 3, and this is just 0. And negative 3 times 1/3 is negative 1. Well, let's see if this makes sense. Here's our graph of x squared minus 4. Remember, we wanted to evaluate it from 0 to 3. So from x equals 0, which is right here, to x equals 3, the average value is negative 1. And that should make sense because most of your values down here are negative. In fact, all of your values from 0 to 2 are negative, and then your values from 2 to 3 are all positive. So you would expect most of your values being negative, that the average value would be negative as well. The last topic we want to talk about is something called consumer surplus. Consumer surplus is basically the difference between what customers would be willing to pay and what they actually pay. Now, everyone should be familiar with the supply and demand curves. Here's your demand curve. It decreases as the quantity increases. And here's your supply curve. It increases. The price increases as the quantity increases as well. We have an equilibrium point here, okay, where the price and the demand and supply intersect, and that's usually the selling price, okay? Now, there's something called consumer surplus, which is over here. If you want to think of this, we know a quantity goes from 0 to Q, right? And we do know that some people are willing to buy items regardless of the price. So even though we achieve an equilibrium price, this quantity over here, the consumer surplus, is what consumers were willing to pay for and compared to what they actually did pay for. Because here's the price. What they actually did pay for was down here in this rectangle. Okay? Now if you want to think about it, if we use this curve, this demand curve here, I can find the area under this demand curve, and I can find the area under the demand curve all the way down to the x-axis. But I can also find the area of this rectangle. And if I subtract the two, that simply gives me the area up here, or the consumer surplus. So this is how we're going to define it. We're going to let A be the amount of commodity available. So in other words, A, we'll just assume for the sake of argument, because our drawings are set up this way, this A is this Q0, or this Q down here. This is the amount, the equilibrium price. It doesn't necessarily have to be the equilibrium price, but for sake of argument, we're going to go ahead and let it be the equilibrium price because that's what it represents on our drawings in this example. Now we know B equals F of A is the current price. So if I have an amount or a quantity, then my demand function tells me there's a certain price that sets in for that demand. This is my B, which is this level here. This is the equilibrium price. Then the consumer surplus for a commodity having the demand curve of P equals F of X. So here's my demand curve. My P function is this. the integral from 0 to a of f of x minus b dx. Well, let's see how this works. F of x is just this top curve, right? I already said that b, even though it's a function of a, is a constant, because a is a constant. A is the equilibrium quantity, or whatever quantity we choose, and b is the price associated with that quantity. So I'm taking my top curve here, my p, my bottom curve, which is a fixed quantity, a horizontal line, and I'm finding the area between them from 0 to this a over here. And that's what this says. This is just the area between the two curves. So if I go from 0 to a, a fixed quantity, of f of x minus b, f of x is simply your demand function, and b is the price that you're willing to sell out of the price that's going to be sold at this amount a. So b is actually the same function evaluated at a. Let's see how this works. Find the consumer surplus for the following demand curve given sales level x. So p is 3 minus x over 8, x equals 16. We know this is our function, integral from 0 to a of f of x minus b dx. They've actually given everything we need right here. Our a is just 16. Remember, a is some value. It doesn't necessarily have to be the equilibrium price. We chose the equilibrium price because it matched up with our drawings. But we could have actually moved that inward and gotten the same answer. If we look back in our previous slide, instead of using this price, we could have gone further in and used a price over here. It still would have been the same concept. I would have gone from 0 to a, and that still would have given me this top function minus my b. So nothing would have changed. So here my a is 16. My f of x, remember, is just my demand function. So this is my f of x is equal to p. And the last thing we need is b, and if you remember, b was just f of a, which in this case is 16, so when I plug in 16 in for x, you get 16 over 8, which is 2, and 3 minus 2 is 1. So now we are ready to sit there and calculate our consumer surplus. This is going to be the integral from 0 to 16 of 3 minus x over 8 minus 1. And before we integrate, we're going to go ahead and simplify this. This is the integral from 0 to 16 of 2 minus x over 8, which we can quickly take the integral of. This is just 2x minus 1 over 16x squared. From 0 to 16, again, we know by now polynomials we don't have to evaluate at 0, so why not just evaluate at 16? 2 times 16 is 32. 16 squared times 1 over 16 is just 16, so 32 minus 16 is 16. Now, please don't assume every time that this answer here is going to equal this x. It just happened to in this function.